In this class, we're going to consider a graphical interpretation of the solutions to quadratic equations. So most equation types are solved by algebra, but there's a graphical interpretation of those solutions. And in quadratic equations, that is particularly true, and it's particularly useful because with quadratic equations, we can generally draw that graphical interpretation quite easily. As you move up to more higher order equations, so powers of 3, powers of 4, etc., or just different types of equation, different types of function in here, it becomes more difficult to visualize it. But for quadratics, it works really quite nicely. And having a visual is a way of validating that the algebra is correct. And the algebra and the visual, the graphics, the graphical interpretation should go together. So they should validate each other. So let's just think about the starting point for this. So we're dealing with quadratic equations. So remember, a quadratic equation is in the form ax squared plus bx plus c. So a quadratic expression set equal to 0. But remember that a quadratic expression written as a function is y equals ax squared plus bx plus c. So this is my quadratic function, and these quadratic functions make U-shaped parabola graphs. So something about those U-shaped parabola graphs, which is always what you get from a quadratic function, is going to play a role in solving these equations. So if we take some made-up parabola like this and just draw it on an xy axis, two of the points that we're really interested in are these ones here. So these points that we call the roots. Okay, so I'm just going to put that on there. So we call these points the roots. If you think about those root points, so because they're on the x-axis, their up and down y coordinate has to be 0. So let's just say that this guy here has got an x coordinate of x1. Then we know that his y coordinate will be 0. And this guy here has got a coordinate, let's say, of x2, an x coordinate of x2, and let's say, and we know that the y coordinate would be 0. So any point along the x-axis has got a y coordinate of 0. So these root points definitely have a y coordinate of 0. So if we just take our y out of here and replace it with what the y value is for these 2 points, it is 0, then that means that these two guys are the same. The only difference is that we've written the 0 on the other side for that top equation. But equations don't care if you read them left to right or right to left, so you can spin the terms around. So basically, just by letting y be 0, we've turned our quadratic function, which was y equals, into a quadratic equation, and the solutions to that quadratic equation are the values x1 and x2. In other words, if I take a quadratic function and I let y be 0, what that is then going to give me is an equation, which if I solve, I'm going to get the 2 root points. Okay, so that's really the link between quadratic equations and the graphs of quadratic functions, and that really gives us a means of making a graphical interpretation of these scenarios. One thing to be aware of, though, is that parabola graphs don't always cut over the x-axis. So you could have a parabola which comes down like this and just floats in space. So basically it turns here, on that turning point is above the x-axis. So that guy doesn't have any solutions if we let the y be 0. It's still got an equation, so y equals, then the equation of the parabola. But when you let that y be 0, like we did here, you won't find any solutions to that equation because the solutions are the point where the parabola cuts over the x-axis. So that guy would have no solutions. Okay, so no solutions. If you've already done work with the discriminant, you'll know that the discriminant is a way that we can determine how many solutions we get for a quadratic equation. If you're not sure what I mean by discriminant, don't worry about it too much. We don't massively need it in this class. You can maybe check out the details of that elsewhere. But basically, we've got this thing called the discriminant based on the a, b, and c values. In this scenario here, b squared minus 4ac, which is what we call the discriminant, would come out to be less than 0, so no solutions. For this guy over here, we've got 2 solutions for our quadratic equation, and the discriminant is greater than 0. There's a third scenario as well though. If you've got a parabola which comes down, and let's say it just touches the x-axis at one single point, that means that you're still going to get a solution. I should actually say over here, oh no, that was fine. I was going to say I should say two solutions. I did say two solutions. And over here, we only get one solution because it is touching the x-axis, but it's not cutting through. So we only get that one point there. So that's the root. So just one single root in that case. So in this case, we get one solution. And for this scenario, the discriminant b squared minus 4ac is equal to 0. So by using discriminant and connecting it with these graphical scenarios, we're already connecting the algebra and the geometry together. And that's what we want to do in topics like this. We want to say, yeah, we're going to solve this by algebra. Sometimes we don't need to refer to the graph at all, that's fine, but to build out our knowledge of the topic, it's great if we can connect the algebra with the graph. So what we're going to do, we're going to look at these two examples. We're going to solve the equations. I'm assuming that you already know how to solve quadratic equations. If not, I'll kind of talk about that as we go through. But then beyond that, we're going to make a graphical interpretation of the solution, similar to what we did over here. So this is a trinomial equal to 0. We're going to solve this by factorizing the trinomial into two brackets. So we get an x and an x. So we always solve quadratic equations by factorizing where they do factorize. If not, then we use the quadratic formula where they don't factorize. But for these ones, they will factorize. So we need a minus and a minus. Minus 4 times minus 2 gives you plus 8. Minus 4 minus 2 gives you negative 6. So that's it factorized. We're then just going to split this off into two mini equations. X minus 4 equals 0, x minus 2 equals 0. Giving us a solution of x equals 4 and a solution of x equals 2. So these points are the x coordinates of our roots. So what that tells us is that if we were to draw this quadratic graph, so this parabola graph, it's going to cut over the x-axis at 4 and at 2. So 4 would be somewhere, let's say, around there, meaning 2 would be somewhere there. We can also get the y-intercept just by reading off that number, so that in trinomial format, the n number is always a y-intercept, so the n number is 8 this time, so the y-intercept would be up somewhere there. And this parabola is going to go down through that point, and then turn back up like that. So these 2 points, 2 and 4, these are effectively the solutions to our quadratic equation, and they're just the points where that parabola, represented by that quadratic expression, cuts over the x-axis. That's all we're really talking about here. We're just effectively finding the roots, but the roots are the solution to the equation. So on the graph, we call them the roots. In the algebra, we call them the solutions or the roots. Sometimes we use those terms interchangeably, but that's all that we're doing there. This guy's slightly different. It's got a common factor type factorizing, so it's not a trinomial, but we're just going to do the same thing. So we're going to factorize it. It's just a different type of factorizing. So 2x bracket x minus 7 equals 0. Splitting this one off into two equations, we get 2x equals 0 and x minus 7 equals 0. That first one gives us a solution of 0, and the second one a solution of 7. So when you've got a trinomial format, you might get two just unique numbers, sometimes only one number, because these can be the same bracket, usually two unique numbers. Over here, when we've got a common factor type factorizing, we always have a 0 solution every time. So this time it's 0 and 7. Those are the two solutions. Those are going to be the two roots of our quadratic parabola graph. So marking on the first one, it's at 0. Marking on the second one, which is at 7. So notice at that point there, 0, 0 is both the x-intercept, one of the roots, and it's also the y-intercept. So we don't need to mark on a separate y-intercept this time. Or you can think of this as being like a trinomial with a 0 on the end. And the number on the end is the y-intercept, so that's another way to think of it. So our parabola this time would come down through those points and go back up like that. Remember that whether this term, the x squared term, is positive or negative determines whether it's a u-shaped parabola or an upside down u. So positive x squared term like this, negative x squared term like this. These are both positive, that's why I knew to draw the parabola that way. So for this one, we've got two solutions of the equation at 0 and at 7, and those are the two roots for the graph. So it's really just about connecting the solutions to the quadratic equation to the root points on the graph, and that is effectively the graphical interpretation. Conversely, if you drew a graph, let's say you used like some graphical method and you drew your graph and your parabola came out to just be floating like that, then you can say that's got no solutions. If you drew your graph and the parabola came and it just touched like that, then you could say that my quadratic equation's got one solution because my parabola just touches at one point. So we're just basically interplaying the idea of the solutions, the number of solutions, with the number and the roots of the graph. So that's really just how we link together quadratic equations on the one hand, which are an algebraic process for solution, and then the graphs of quadratic functions on the other hand, which just kind of show you those solutions on the graph. And the key is really just recognizing that the solutions of the quadratic equation are just the roots of the graph, and then just filling in the rest of the graph. It's really tying together the algebra and the geometry. So you might get questions where you don't have to draw graphs. That's generally true. It's usually just working to this point. But as you go further into this topic, and as you use this type of material in future classes, maybe all the way up to pre-calculus and then calculus classes, you'll find scenarios where you'll be drawing graphs more often. As you get further into functions, you'll not only want to do this as an algebraic process and stop here and say, yay, I got my solutions, but you might want to actually interpret those on the graph. As you move up to higher orders, like an x cubed, an x to the power of 4, stuff like that, it's going to be more important to learn to tie the algebra and the graphs together. So this is about kind of building a little bit for the future and just to round out your knowledge on this topic. So have a go at solving some quadratic equations, but take it a bit further by just plotting the graphs like I did there, and it will just allow you to put together those two different areas and ways of interpreting these questions.